Hello everyone, and welcome to today's presentation as part of the Lunch and Learn series offered by the Engineering and Operations Management Department at the University of Arkansas. My name is Karen Hickenbotham, and I am the Program Manager in the Operations Management Program. As part of the Industrial Engineering Department, our department does offer 3 online degree options. And we have a Master's of Science in Engineering Management, and in Operations Management, and we will touch base on this after the presentation. So for today, I am proud to introduce to you Greg Hutto. And Greg serves in the 96th Test Wing as Chief Operations Analyst, responsible for embedding design experiments as the principal test method for several hundred tests each year. He teaches an extensive series of short courses in test methods to all testers in the wing commander to our 600-plus scientists and engineers. As a lieutenant colonel in the United States Air Force Reserves, he serves as senior military advisor to Air Force Operational Test and Evaluation Center and as special advisor to the test design to the Flight Test Center commander at Edwards Air Force Base, California. Mr. Hutto is a distinguished graduate of the U.S. Naval Academy in Operations Research and holds a master's in the same field from Stanford University. Over the past 30 years, he has served nearly every branch of test and evaluation from laboratory basic science to joint operational field testing. He would like to publicly repent of his 11 years of testing without the benefits of the principles of well-designed experiments. Everyone, I am proud to introduce to you Mr. Greg Hutto.
All right, so I was mulling over what joke to start with. That's why I did the poll, and since we had majority mathematicians, I thought I'd start one off. But in order to set that up, I want to remind you of Zeno's paradox. The philosopher Zeno, in about 450 BC, had a paradox about arrows flying toward walls. They have to fly halfway there, and then halfway there again, and halfway there again. And if that's true, then they can never reach the wall. So the joke goes like this: an infinite number of mathematicians walk into a bar. The first one, somebody's changing my slides around here. First one orders half a beer. First one orders 1 beer, the second one orders half a beer, the third one orders a quarter of a beer, the fourth one orders an eighth of a beer, and so on and so forth. After a little while, the bartender rolls his eyes and sighs and says, "Here, you guys work it out. I've reached my limit," and he pours 2 beers. Okay, so that's joke number 1. The second one, since we're going to be talking about elves and sprites today, I thought I would come up with a elf and sprite joke, and it goes like this: a Republican, a Democrat, a communist, a priest, a rabbi, an imam, an African, a Caucasian, an Asian, a horse, a giraffe, an elephant, a unicorn, a fairy, and a sprite walk into a bar. See? The bartender looks up and says, "What's this, a joke?" So, all right, so moving along. What we're going to do today is talk about a different approach to statistics rather than the theoretical approach that we've often learned, usually based on normal theory and some other ones. So I'd like to introduce this idea of resampling statistics, and it's based on doing statistics by experiment. So to get in the spirit of doing that, I ask you all to bring a coin. I hope that you did. And I'm going to set up a poll here, and I want you to flip your coin twice. And when we do that, I'd like you to vote for me with the 2 coin flips that you get. So I'm going to ask you to vote your families here. So if you flip a head and a head, you'd vote male, male. If you flip a head and a tail, you'd vote male, female. If you flipped a tail and a head, you'd vote female, male. And then finally, if you flipped tail, tail, you would vote female, female. All All right, so let's take a moment and vote those if you don't mind, and I'm going to go ahead and flip mine. I got a tail. I got another tail, so I would vote female, female down here. There's my vote. That is quite a skewed vote. All right, I've still got no response from 22. This is supposed to be an interactive webinar, so if you can vote, I'd sure appreciate that. Okay, so I'm going to lock it there, and it's not really helping my case here, so I'm going to dismiss that for the moment. What I had expected to see is more of a uniform mixture. There's about a 1/4 chance of getting any one of these outcomes: male, 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 female, female, male, and female, female, given that there's a 50-50 coin flip of heads and tails. So when we wanted to estimate the probability of one boy and one girl in a 2-child family, easy to do with a Monte Carlo experiment, we flip a bunch of coins like that, and we count the number of 2-child families that have exactly one girl, and that number ought to approximate 50%. Now, a little bit more difficult problem is this one. Given that one child is a boy in a 2-child family, what's the probability that the other one is a boy? So think about that one for a moment. If you think about that one for a moment, you might be inclined to say that the probability is 50-50. But in fact, you'd be wrong, because if you're given that one child is a boy, you've eliminated the possibility of a female family. So all you have is the male male, the male female, and the female male family. So if you know that you got one child and a boy, the probability that the other child is a boy is actually 2/3. So, and again, we could work that out with experimental methods rather than doing the standard probability that we learned in a probability and statistics course. Okay, now for a harder problem yet, I'm going to introduce the Monty Hall problem, and I will give you the answer to this at the end of the seminar to give you a incentive to hang out here and see this. So here's a Monty Hall problem, and it's obviously after the let's make a deal. And so Monty Hall is standing in front of 3 doors. He asks you to pick a door, and at random you pick door number 1, door number 2, or door number 3. After you pick the door, Monty asks you to he'll open the door, and show you a goat. So behind one of the doors is a goat, and the other door is a new car. So he asks you, having shown you the goat, do you want to stay or switch? And so what I'm going to do is set up another poll here, and I'm going to ask you to vote on this one. You've got 3 choices. You can stay, you can switch, or it doesn't matter. All right, so the first answer is stay. The second answer is switch. And the third answer is doesn't matter. And I'm going to start that poll, and I'll let that run for a few minutes here as we move along. So I'm going to move along here, and hopefully that's not going to get in the way of the flipping slides. Doesn't let me move this thing around. All right, so I'm going to move. There we go. All right, so this, there we go. Let's me move to that. So here's back in, and I hate to say it, 1976. All right, I got 8 stay, I got 22 switch, and 6 say it doesn't matter. So we have 8 stay, 22 switch, and 6 it doesn't matter. All right, so I'm going to cut the polling off there. I've still got 31 with no responses, but we'll press on. I'm going to clear that poll out. And I have Dr. Parnell has raised his hand. Something over in the chat. Greg, is there something you wanted to say? Do you want to send something to the chat? Okay, so long time ago, back in the dark ages, I took statistics, and this is the way. This is the actual chapter headings for the first course in probability and statistics. But we learned about sampling distribution and point estimates of parameters, means, medians, standard deviations, variances, modes, all these sorts of things. We learned about creating statistical inferences, intervals, like confidence intervals for single samples. We learned about single sample hypothesis testing. We learned about the student t-test. We learned about the testing proportions and so on and so forth. And then we moved on to making statistical inferences about 2 samples, differences in means, differences in variances. We learned about the paired t-test. And then you may have learned about differences in proportions as well. So moving along to the next slide here, I dug through my old course notes and came up with my course notes from that class in probability and statistics. And most of us learned it that way. We learned, of course, Dr. Carrie Beam teaches a really great probability and statistics course using this textbook from Montgomery and Runger. So is there not another alternative to learning statistics? And that's what I intend to go over today. So let's move along. So let's introduce a problem. We need a problem here to solve so that we can use it. So here's our problem. We have some elves frolicking deep in the woods in the forest of Nod, and they had a frolic fest recently in which they imbibed the elixir Elsinore, and they danced and frolicked for an average of 30 hours before needing another elixir to recharge. So the elves are righteously proud of their frolicsome fortitude, say that 5 times fast, but not all of them frolic equally. We want to ask, how strong is the evidence that these elves can frolic for an average of around 30 hours? Might the average be substantially more or less in future frolic fests? And so we'll call Tim the Enchanter to come in and adjudicate the question. So here's our data set. We have a single estimate of the average frolic time. So we have 20 frolickers here. You can see, and there's our frolicsome elves, and there's a number of hours that they frolic before collapsing and needing another elixir. We can calculate some summary statistics for this. We can calculate the average and the standard deviation, the median, the range, the 90th percentile. We can measure skewness and kurtosis. There's all kinds of statistics we can compute from this sample, but what we're interested in is not just what information this sample holds. We want to ask ourselves, what might future samples look like? How big might the average be? How small might it be? And as I look through this sample, I can get some evidence about that, right? The smallest number I see in here is something around 24, I believe. Yeah, there's a 24 right there. The largest number I think is somewhere around 36. So we would certainly be surprised to see an average in future Frolic Fest smaller than 24 or larger than 36. But how about 28? How about 32? What numbers might be reasonable and what numbers are less reasonable? So the obvious solution to that is to go get some more data, right? So we'll go attend more Frolic Fests and gather more samples of 20 and then compare them, and that will give us an idea of how variable this 30 number is that we got in our single sample. But, and here is the key, this is the big turning point in this whole lecture. If I am willing to assume that this sample of 20 represents the original population that's unknown to me in terms of its shape, its center, its dispersion, and so on and so forth, all the important aspects of the population that I want to make statements about, how about I just reuse this sample? I've already got 20 samples there. How about I draw samples with replacement from this set of 20, and then I keep track of the average. So this slide shows 6 samples plus the 1,000th one over here. So in my first sample, I have these distribution. In this sample, I have this distribution. That large 36 I see in some of the samples, I'll have 2 or 3 36s, and some of the samples I might not have any. And so this variation from sample to sample is going to give me a distribution of averages to look at. Let's see what that might look like. So I already did that, and I'll show you at the end of the session here how that's done mechanically. We'll use a add-in in Excel, although there are a number of other ways to do it. If we look at that sample of 1,000 resamples from the sample of 20, I get a distribution that looks like this. It's centered, not surprisingly, on the original average of 30. If I go back here, I'll notice that original average was 30. There it was. I'll also keep in mind that standard deviation is around 3.1, so that gives me a variance, a square of that around 9. Those numbers in the back of your mind, we'll need those here in a minute. All right, so what I can see is that this distribution of averages, the 1,000 averages that I drew from that sample, they center around 30, and that's not surprising. But I can also make some other comments. Look at the shape of that. Have we ever seen that shape before? That looks very much like a doubly inflected bell shape, like the normal distribution. It shows me what unusual averages would be: an unusual average above 32, usual average below 28, and I can calculate the variance of this, and it turns out that the variance of this sample distribution here is about 0.44, which is very, very similar to the variance of the original sample divided by the sample size, 20. Anyone remember what the central limit theorem says? The central limit theorem says that the sampling distribution of the mean, as n increases, is normal. It has the mean of the population mean, there's 30, and it has the variance of the population variance divided by the sample size, n. So one could make this as an illustration of the truth of the central limit theorem. But we can use this to do some other things. Before I get to that, let's look at a couple of other points about this resampling. You may or may not remember that I had to wait for my slide. You may or may not remember that the sampling distribution of a variance is a function of the chi-square distribution. There's a theoretical chi-square centered on n-1. There's a bootstrap sample of the population of the sample variance that I just did, and they look suspiciously alike. So what another cool aspect of the bootstrap is, I can bootstrap the sampling distribution of any sample that I can, any sample statistic that I can compute from this sample. I could compute proportions, medians, ranges, percentiles, any function of the sample that I can compute. I can generate a sampling distribution of that. So what can I use this sampling distribution for? Well, it's the same thing we used in normal theory. The first thing we are usually taught about doing with the sampling distribution is to use it to calculate confidence intervals, and the second one is to do test of hypotheses. But before we get to that, let's talk real briefly about the mechanics of how this is done. In Excel, I simply select this set of data here. Here's my 20 samples. And I select that. I click on a toolbar that this Resample Stats add-in gives me. I click on the R, that samples with replacement, and I put the resulting value over here in a template that will hold all of my resamples. Then the second thing I do is I tell it to keep track. There's a RS button here that says repeat and score, track of this score cell. In this case, I wanted to look at keep track of the sample average. So that's all there is to the mechanics. I have a question to answer. What are likely and unlikely values of the mean? I have a function that answers it. There it is. There's a sample average. I've told it how to resample, in this case with replacement, and how many resamples to do. And I can tell it, in this case, I did about 1,000. We'll talk a little bit more about that going forward. All right, so that's the mechanics of how it's done with this resampling tool. And as I move forward here, I can use that sampling distribution of the mean here. Here's the sampling distribution of the mean. I can actually look at those 1,000 samples, cut off 2.5% on the bottom and 2.5% on the top. That'll, out of 1,000 samples, that'll be 25 each. That will leave me 95% of the samples in the middle. And we've already made the observation it would be surprising if the true population mean based on this sample was outside of 28 or 32. But I can say that 95% of the time that the true sample mean probably will lie between 28.75, that's the lower 2.5 percentile, and 31.25, which is the 97.5 percentile of this distribution. The way I could also look up, if I sampled individual values, I could look up a prediction interval, and if I sampled individual values many times, I could look up tolerance intervals. So I can create all kinds of statistical intervals with this same simple approach to the Bootstrap or resampling. The next thing I can do with this is to actually, I'm missing a slide. Huh. Maybe, I guess it's a couple of slides forward. I'm sorry. I have one more topic on this single sample. All right, that was the sampling using the sampling distribution of the mean to calculate a confidence interval. I still need to do a one sample t-test, and I'm doing fine on time here. I've got about 20 minutes. That's the big idea already introduced. Now I'm just going to add some refinements to it. Here's a history of resampling. You might remember the great French philosopher and mathematician and physicist, a guy named Blaise Pascal. He was able to convince noblemen to be his patron as long as he worked out the rules for gambling. What are the best strategies to use in baccarat and roulette and all the games of chance that they were playing back then? Unfortunately, the Bernoulli brothers hadn't been born yet, and so he didn't have a theory of probability. And so you may remember in the sum of two dice, the most likely value is 7. and that was calculated by Blaise Pascal using what was known as Pascal's triangle. You have a single way of rolling a 2 or a 12, and you got about 6 different ways of rolling a 7. And so 7 is the most common outcome, the most likely outcome, where 2 and 12 are the least likely. And that gives you some rules experimentally produced on how to play dice games. So later on, the Bernoulli theory the Bernoulli brothers added probability theory. Gosset introduced the t-test in 1908. Fisher introduced experimental design in the 1920s. In the late 50s, Rand, using the UNIVAC, introduced Monte Carlo approaches to statistics, and a guy named Quinnell and later John Tukey introduced one of the first leave one out sampling methods called the jackknife in the late 40s to the mid 50s. And then a guy, Julian Simon, you may have not heard of, more known as an economist than as a statistician. He introduced resampling, he says, to teach probability statistics because he despaired of finding ways of teaching this that people could retain. And so he introduced the bootstrap and what he called the shuffle in the 1960s to teach probability and statistics to doctoral students in business and economics. One of my alma maters, Bradley Efron, in 1979, launched the bootstrap on the mathematical statistics world with an article from Scientific American, and Peter Hall published one of the first textbooks on the bootstrap in the 1990s. There's a number of them out there available right now. So bootstrap and experimental approaches to statistics have a long history. So you can rely on the fact that these have been vetted and they work actually quite well. Okay, moving forward. You may wonder where the name Bootstrap came from. The Germans have their own Paul Bunyan story, a guy, Baron von Munchausen, and the Baron was said to have told this story to a lady admirer. He fell out of his boat in the middle of the lake while fishing. He was wearing some body armor at the time, and the lady wondered how in the world did he save himself, and he said it was simple. I simply reached down and pulled myself up by my bootstraps. And that kind of sort of seems like what we're doing when we are bootstrapping the original sample data. We're somehow getting something from nothing. So if this is Gosset's resampling paper. In March of 1908, he published a paper known as The Probable Error of a Mean, published by a gentleman named Student. He says, you might remember, one of the brewmasters and experimental statisticians for the Guinness Brewery in Dublin, Ireland. And Guinness didn't allow their scientists to publish by name, but they gave him permission to publish this great finding that led to the 1 and 2 sample student t-test under the pseudonym Student in the journal Biometrica. All right, so and he actually estimated and invented the student t distribution by drawing thousands of cards with samples of size 4 written on those pieces of cardboard. He did this over and over and over again, plotted the resulting mean divided by the variance, and he found out he had a normal distribution with fat tails, and that led him to work out the sampling theory that led to the student t distribution, which we all know and maybe don't remember so well from our probability of statistics days. But with the bootstrap, we don't need no stinking tables. We don't need no formulas. All we need to look things up. Hopefully that's the next slide. If we wanted to test a claim about a number, suppose that while the elves were, we're changing the problem up here. Suppose the elves had imbibed the new and improved Elsinore elixir. That's trademarked, by the way. Can we support that Elsinore extends the frolic time from the usual value of 30, which we've seen in the past, to as much as 32 hours? Does this sample of data support the claim that Elsinore elixir is better for frolicking than if the old formulation of Elsinore alone? So in other words, can we take that sample data and does it support a claim of 32 hours? We would do that with a single sample t-test, but with the Bootstrap, all we need to do is look up that 32 value in the sampling distribution. Here's that sampling distribution of the mean, again, with a sample mean of 30 there, with the same variance that we've talked about. But if we take all of the 1,000 samples here, and we look up the number 32, this shouldn't extend into this diagram. The 32 is intended to be the cutoff right here. You can see how many values were equal to or greater than 32, and it's easy to calculate that. We just add up 1 plus 2 is 3. So how often did we get a sample mean of 32? I repeated Bootstrap sampling from our original sample, and the answer is not very often. In fact, 3 in 1,000. Can we use this for our p-value? Well, in fact, if we actually did the single sample t and we calculated the t statistic of 30 minus 32 divided by the pooled standard deviation divided by the square root of n, we'd end up with a value of minus 2.90. Looking that up in the student t reference distribution, we have p of 0.005. So excuse me, 5 in 1,000, not 3 in 1,000, but remarkably close, right? In any case, we would say thumbs down on the claim for the new Elsinore that it made my frolic time as much as 32 hours. So again, one of the great advantages of the Bootstrap is all I need is a computer-intensive capability, and I can look the number up without having to rely on a lot of theory. All right, moving on. We need to crank up to 2 samples now, and that's as far as we'll be able to go today. So now we're going to change up the problem again. We're going to use elves and sprites. And so what we do here is we're going to have a frolic off between the elves and the sprites and ask who is more frolic, the elves or the sprites. So let's move on and see about that. So now we have a frolic off. We have 10 elves, 10 sprites. They frolic together until they can frolic no more. And we calculate the average of the 10 elves and the average of the 10 sprites. We use that same kind of mechanics here. We have, so it's like 29.9 for the elves, 27.5 for the sprites. We take the difference, elves minus sprites, we end up with a positive value of 2.4. Stick that in your memory. We'll need that in a minute. 2.4. All right. Then what we're going to do here is we'll draw samples from these 20 samples here. Again, this time we're going to not use the R with replacement. We're going to use S without replacement. And what Simon called a shuffle. We're going to take these, write them all down on pieces of paper, shuffle them together, and deal them out. 10 go in this column, 10 go in that column. So shuffling without replacement, I exactly mimic these 20 values in each of my shuffled samples. Then again, I will keep track of the difference of the elves minus, I changed out fairies to sprites so that it would be less offensive. So elves minus sprites here, my first shuffle sample was 0.4, not the original observed value of 2.4. So now I want to say, is it possible that the true difference between elves and sprites is really zeros? It was just a matter of chance, a matter of noise, that I observe a difference as big as 2.4. All right, let's, we have to go through and do this this, do a shuffle this time. We're going to shuffle this 1,000 times into this template, keep track of the difference that we observe in our 1,000 shuffles this time, and see how often a value of 2.4 or more occurs. Now, if you think about that process for a minute, the average is going to be 0, right? Because I'm shuffling them together as if there's no difference between the two columns. And so when I do that, the average between the two columns over 1,000 trials is going to be 0. And I come over here and I get the difference. This is not now the sampling distribution of a mean. This is a sampling distribution of the difference between two means. And you can see, again, it's centered about on 0 here. And out here in the tail, I get a value of about 2.4. All right, and how far out in the tail? Well, about 44 times out of 1,000, or about 4% of the time, I get a value of 2.4 or greater. If I were to do the two sample t-test and actually calculate the difference between the two means, I get a value of minus 1.88, and I get a p-value of 4 in 100, or about 39 in 1,000. Again, in remarkable agreement, since this p-value is low, I would reject the null hypothesis that the two are the same, and instead I would say this value 2.4 is likely to be based in cause and effect, and not just a product of noise. So I would say that the elves in general frolic more than the sprite do. And again, I don't need a formula to know that. And I can make probability statements about how likely it is that I would get a difference as big as 2.4 if I treated them as two samples were the same. Again, without any need for formulas, tables, Excel functions, or statistics packages. All right, moving along. I can actually do a sampling, a confidence interval for the difference between the two. And so what I'm going to do is now I'm going to draw samples within each of the two columns. Why am I going to draw within the two columns? Let me go back 2 slides here. One more slide. I'm going to sample within the two columns because I've concluded by my shuffle test that they're actually different. So elves stay with elves, sprites stay with sprites, and I'm going to draw samples with replacement this time within each of the two columns, and try to build a confidence interval around this difference of 2.4. So by respecting the within column values, I generate this. It's centered, not surprisingly, on 2.4, but it might be as high as 4.8 or as low as 0.2. That would be a 95% interval that would contain the true difference between elves and sprites frolicking 95% of the time. So again, I can look up that interval estimate without need for any formulas. Okay, so we have spent about 25 minutes, and we have covered basically the difficult part of a semester's worth of statistics. We looked at the sampling distribution of the mean. We looked at the sampling distribution of the variance. Sampling distribution of the mean is normal. Sampling distribution of the variance is a function chi-squared. We built a confidence interval. We talked about prediction and tolerance intervals for single samples. We did a single sample, one sample hypothesis test for the single sample t-test, and we did statistical inference for two samples. We did the difference in means, but we do exactly the same mechanics for differences in variance, differences in proportions, difference between any two functions I can compute of two columns, and by restricting how I draw my samples, I can do even a paired t-test with the bootstrap and the shuffle, plus intervals for the two samples. So I'm going to relax there for a second, take a sip of coffee, and let you just think back on how much statistics we covered in 25 without a single table or a formula or me drawing a normal distribution on the board. All right, a little bit more. Here's some definitions. Bootstrap is statistics done under the assumption that the population distribution is represented by the sample distribution. That is the single but key assumption of the Bootstrap. But you know what? Any statistical manipulation of the data is making that assumption, that the sample data that we have represents the population in the important characteristics that we are testing. Every statistic makes that representative assumption, and that's why we are so big on random sampling, so that we can get independence and representativeness in our samples. All right, permutation shuffling methods. This is the basis for something that you may know of, but probably don't if you're not a real guru in statistics, something called Fisher's exact test. Fisher, as usual, did an astonishing amount of calculation. He actually counted up every possible shuffle of samples and computed how often, if you shuffled all the data or permuted all the data together, you would get a difference as big or bigger than the observed difference. That's called Fisher's exact test. It's hard to do on samples where you got more than 6 or 8 samples each, because the number of permutations just gets out of hand. But if we sample without replacement, the shuffle, we can say we're basically asymptotically estimating the value of Fisher's exact test, and you can do the sampling with replacement. The Bootstrap is an approximation of the shuffle. So resampling is a whole field of statistics, very popular nowadays. And then again, we're using a variation on Monte Carlo statistics or statistics by experiment. All right, a couple more things. It's pretty cool to teach a bunch of different statistical concepts via resampling. What do we mean by a significant difference? What are we talking about when we're estimating percentiles? The median, the 75th percentile, the 10th percentile, the 90th percentile. We can bootstrap that. Computing alpha and beta errors in hypothesis testing. We can bootstrap both the alpha and the beta. We can, as we've seen, done confidence intervals. We can calculate operating characteristic curves with the Bootstrap. We can do correlation and regression coefficients. All of those with that same similar approach. And what I really love about resampling is a lot of people have very fuzzy thinking when it gets to doing with statistics of exactly what they're doing. They grab the statistics software nowadays, slap some numbers in, read off the p-value, and hope they got it right. Very often we got some real fuzzy thinking going on. What the Bootstrap and the Shuffle do, it forces us to think through the problem. Exactly what question am I asking? What calculation will give me the answer? And how should I draw my repeated samples in such a way that the result of the resampling will give me the answer that I'm looking for? All right, just a little bit more. It's not a panacea. There are some drawbacks to it. I've seen people bootstrap sample sizes of 3, which is absolutely ludicrous. We can gain no more information than we have in the original sample, and so you need a reasonable sample size. I use sample sizes of around 20. 15 is probably on the lower limit of a sample you'd want to bootstrap. Below that, you're risking a lot of errors due to inadequate distribution and variability in your sample. This one's really not a trouble. You can do thousands upon thousands of bootstraps for shuffles. If you have questions about whether you've drawn enough bootstrap samples, do more, and it'll actually reach a limit asymptotically as you continue to draw more resamples. If the data we are starting with is non-representative, you can bootstrap that all day and still get the same errors you would get if you weren't using the bootstrap, you were using classical statistics. So this just gives us yet another good reason to have draw our samples in such a way that they represent populations we're targeting. And then this is a little bit tricky. When you're estimating a tail percentile, like the 90th percentile, you need both originally a large number of samples, say 50 or more, and you need to bootstrap it many, many, many times to get an adequate estimate of the 90th percentile. So if you got a tail percentile to estimate, come see me and we'll talk about how to take care of there. So there are some drawbacks, but by and large, Bootstrap and the shop work great. All right, we're moving along here. Here's some references and resources. I'll leave these in the slides. These are links I looked up for you. You can do all of this within Excel using index and random functions. This is a really cool little article from realstatistics.com without any other tools than just basic Excel. So take a look at. I used the Julian Simon's resampled.com. I'll demo that here in just a minute if we have a little time. And now I'm done. So this is statistics without pain, without need for a bunch of formulas, a bunch of normal distributions, a bunch of asymptotic theory and tables and all that sort of thing. There's one of my heroes, Julian Simon, author of Resampling Stats. Again, being an economist, he really didn't get notice out of the statistics community in the 60s when he introduced resampling stats, but he's a pretty cool guy. All right, so it provides us a method that's simple to teach and use. Couldn't be simpler than what I just went through. It's robust against violation of assumptions. I don't need a normality assumption. I don't need an equal variance assumption. All I need is a representativeness assumption. It can be somewhat resistant to misuse. It can help us with missing data. It deals directly with the problem that we're addressing. We don't have to malform the problem in order to fit our toolbox. And then it can help us to illustrate and understand otherwise difficult to understand statistical concepts. So I highly recommend you add Bootstrap to your tool bag today. All right, so I'm done exactly on time. As I promised, I'm going to let you guys type a few questions in the chat box if you like. I'll wait for a minute or two. Karen's got a couple other slides to show you, and then I'd like to illustrate the Excel file and how it actually works, the mechanics, if you'll hang around for a few minutes. Karen, over to you.
Well, thank you very much, Greg, and thank you for being with us today. And if you do have any questions for Mr. Hutto, please feel free to type those in the chat at the bottom of your screen, the little bubble there. But while we are waiting on some questions.
Sorry, Karen. I'm sorry. I have one more slide. I forgot. I promised you the answer. We had 8 people say stay, 22 say switch, and 6 says it doesn't matter. Well, it does matter. If we do an experimental statistics in Excel and do 1,000 games, if we stay, we'll win 1/3 of the time. If we switch, we'll win 2/3 of the time. And so it certainly pays to switch. And if you don't believe me, I'm happy to argue with you over email. So sorry, back to you, Karen.
That's quite all right, Greg. Thank you very much. So while we are waiting for any questions to come through, we've put on the screen there Mr. Hutto's email. If you have any questions for him via email, you can privately message him there. But in the meantime, we can go ahead and take a look at, if you kind of like what you heard today, this is just a sample of the the kinds of topics that we have in our classes and our programs, the Masters of Science in Operations Management. Okay, I'm going to pause there. We have a question come through. Greg, I'll go ahead and let you read that and take over.
All right, I'm back. The question is, the question is, any comments on the multivariate bootstrap? All right, so multivariate, we did 2 samples. That's multivariate, not big multivariate, but it's 2 multivariate. If you're talking about like multiple regression or multiple sample ANOVA, it works just fine. If you're talking truly about multivariate statistics like discriminant analysis, principal components, when you have a matrix for the X and a matrix for the Y, to be honest, I have no experience with the bootstrap and multivariate statistics, but I'm absolutely convinced that there are variations on the bootstrap that would apply there as well, with again the cautions about adequate sample size to bootstrap from, and the caution to have representative data. But that's always true in any statistics. I don't know if that's helpful or not. You're most welcome. Check out some of the textbooks. There's a bunch of great textbooks out there. All right, so we got just a couple of minutes left. Karen, if it's all right, show them the Excel.
That would be fine, Greg. Go ahead.
All right. So I'm going to go over here. I'm going to share. I'm not going to share files. I'm going to try to share an Excel. Let's try that. Oh, that's a screen. Sorry. Let's share. Where's my Excel? No. There it is. All right. So there's my Excel. I'm going to drag that over to this screen. Is that going to work? And the reason I'm dragging it over to this screen is so that I can see it and look in the camera and not be looking 90 degrees off, which is always a little disconcerting. All right, so let's look at the mechanics. Here's our 2 samples. Here's the 2 sample t-test I did in Excel. And so what I'm going to do is, here's my original data set here. I have a difference of 2.4, the difference between these 2 cells here. And all I'm going to do is draw repeated samples out of here over into this template, and I'm going to keep track of this difference over here. All right, so let me go ahead, go to the add-ins here in Excel. I'm going to reset everything. There's a reset button here, and it says all the variables have been reset. I'm going to grab the original data, and then I have 2 choices. I can sample with replacement. The drawback of that is that there's a sample with replacement that is all 33s. There's a sample with replacement that's all 26s. So some of the samples with replacement are not representative of the original sample here. If I sample without replacement, 33 only appears the number of times that it does in this set of 20 values. So I get an exact copy of this, just in different columns. That's what a shuffle does for me. So some people would argue that the shuffle is a more accurate method of resampling than the bootstrap, but both of them are going to give you very similar answers. So it just depends on which button you push here, whether you sample with replacement, the bootstrap, or sample without replacement, the shuffle. I'm going to do it without replacement. Click on that. It says that's fine. Top left cell of the output range, I want to put it over here in my template. It will repeat this pattern over here, and I say okay. There are lots of different shuffles I can do there. No time to talk about that today. And let's just keep track of this difference. I originally observed 2.4. When I shuffle them together, I reverse the sign, and now it's 2.6 the other way. So this 2.4 not looking so big right now because I reversed the sign and went the other way. But let's do this lots and lots and lots of times and see how often this 2.4 appears. So I do repeat and score, RS, keep track of that. That's over here. And it says how many times do you want to do it? And the answer is 1,000. And so while that's going on, you can't see it, unfortunately, but down here in the status bar, I didn't drag the Excel up far enough, it's counting the number that it's done. And because it's busy, I can't drag it up, but you can see it doing the shuffles. It took us all of 16 seconds to do 1,000 shuffles, so not very expensive. There's a new set of shuffles. Let me show you what the result looks like. I cleaned it up a little bit. And then all I did was I cleaned that up a little bit. I made it a little bit wider. I originally saw that difference of 2.4 that occurs out here. If I look up 2.4 in this distribution, I can look it up exactly over here just by sorting this, right? I just go home. I can sort from, let's do largest to smallest. That'll put the 2.4 up near the top. And if I look down here, where does 2.4 occur? The 2.4 or larger, where's the first one? There it is. It's 487. So that we'll call that, I'm sorry, that's the most common value because we, no, I'm sorry. I made a mistake there. What I showed you here is the difference between the two columns. I bootstrapped that. What I did when I did the actual bootstrap here was I was testing the difference between the two columns. So apologize for that. What I saved was keeping each set within their column, and that was the bootstrap that I showed here. This is the difference between elves and sprites. Its average is 2.4, and you can look up the cutoff 25% here. That's 3.6, and then on the other side, I want 975. I'm sorry. 975. That's a little ways. There it is. So that's 2.6 on one side and 225 here, which is there, 2.8. So that will be my confidence interval around the difference between the two columns. Okay, well, thank you all for your attendance today. The resampled.com has a very inexpensive ad in here. I think it costs $99 for a year, and there's actually a student version that you can get. And I'll hang around a little bit and see if there's any more questions. I see a couple in the chat. Carol said, thank you. And I say, you're welcome.
Well, while we wait for a couple questions, I just want to announce that we have another webinar coming up in 2 weeks on April 16th. It is entitled When Optimal Isn't Optimal, presented by Dr. Robin Burke. She is a speaker, best-selling author, consultant, and expert on the disruptive tech that is rapidly changing our world. A very relevant topic, I should say, right now. That is coming up on April 16th. You can register on our website. Yes, I think Lisa was commenting that a very relevant topic indeed with our upcoming webinars, and we will strive to continue to do so. Well, we'll go ahead and conclude the presentation. Greg, thank you very much for your time and all of your effort that you put into this. We all really do much appreciate it. And
That was
everyone stay safe and healthy, and as we all adjust to our new normal.
you bet. All right, Karen, thank you.
Thank you.
Bye.
If you enjoyed today's presentation, that's just an example of the types of topics that we do cover in our program and in our courses. We have a Master's of Science in Operations Management. We have full online and live course options. It is 30 hours of credit required, which equates to only 10 graduate courses. There are 4 prerequisite classes that possibly can be waived depending on previous coursework. There's our 5 8-week sessions per year. There are no GRE or GMAT test scores required as long as you have a 3.0 bachelor's GPA. The total cost of the program is about 12 to 15,000, depending on the amount of prereqs that are needed, and it can be completed in 1 year, but you have up to 6 years to complete. The other offerings that we do have, we have a project management graduate certificate. We, again, have online and live course options. It is a total of 4 graduate courses equating to 12 credit hours total. We do, again, still have the 8-week sessions. There are 5 enrollment periods throughout the year. The entire cost of the certificate is approximately $5,000. The only requirements to enter in the certificate is to have a 2.5 GPA with a bachelor's degree required for admissions. The benefit of this certificate is if you do decide to continue on into the Master's of Science program, all 4 of these courses can and will count towards an MSOM degree. Everyone, thank you again. The information about our program, you can reach me, Karen Hickenbotham, and there is my email address on the screen. The video from today's webinar will be available on our website, and registered participants will receive an email with the video link. Again, registration is open for our next webinar on April 16th with Dr. Robin Burke on our website. Good day, everyone.